Hi guys, this is section 5.2 mathematical induction. This is one of the essential sections because this technique allows us to prove statements that are true for all n, basically formulas. The idea of this mathematical induction is actually pretty simple and intuitive. Basically, it involves two-step process. The step number one is the basis step. That means you prove first thing is true. So this is pretty generic, okay? And the step two is the inductive step. That means assume the thing is true for k, then your task is to show that it is also true for k plus 1. If you are able to do so, then the statement is true for any k. Now, if we want to look at an analogy, so for instance, this is a ladder. There are infinitely many steps on this ladder. So if you are able to prove that you are able to climb on the first step, which is the basis step, okay? So prove that you are able to climb up on this first step. And the second thing that you want to prove is assume that you are on the kth step and you are able to climb up to the k plus first step. So in other words, if you assume that you're on the kth step and you can show that you can climb up to the k plus first step, then automatically this completes the proof that you are able to climb up to any steps. The reason is if you are able to prove that when k is true, you can prove that k plus 1 is true, then you can imagine. So when k is 1, right? When k is 1 here, then you must be able to climb up to k plus 1, which means the second step. Now, of course, when you're in second step, because you already proved that you can climb up to the next step, like the third step, and so on and so forth. Basically, you can climb up to any ladder, any step that you want. So that statement will be true for all k. Well, the book does provide like using the domino as an reasoning. So to me, that's pretty helpful to help you understand the idea of this mathematical induction. So again, let's look at the principle of mathematical induction, which is named by De Morgan back in 1883. Let Pn be a property that is defined for integers n, and let A be a fixed integer. When the following two statements are true, the first one is this: assume Pa is true, where A is the smallest integer that makes the statement true. Oftentimes, not always though, this A is usually 1, of course. Sometimes can be other integers. Now, so first of all, if this is true, of course, you have to verify that it is true, right? And second, if for all integer k greater than or equal to this this A, which is the smallest integer, that makes the statement true. If pk is true, then pk plus 1 is true. So you have to show that this statement is also true. If you show that both statements are true, then you can make a conclusion that for all integer n, Pn is true. Now, how does that work? We're going to look at the proof of this formula to show how it works. But before that, let's make sure that we make sense of Pa, Pk, Pk plus 1, okay? So let's consider this formula. We are going to prove this formula. This formula says 1 plus 2 plus all the way up to n is equal to n times n plus 1 and then divided by 2. Now, the P1, P of 1, that means P of 1 is when n is 1, is this is the statement, okay? So when n is 1, that means this. That means left side is just 1. You want to stop at 1 because when n is 1, you begin with 1. The last number you want to add is 1, which is basically just one number here on the left side. And the right hand side will be 1 plus 1 plus 1 times the quantity of 1 plus 1 divided by 2. So that's basically P1, P of 1. Okay, this is P of 1. Is this true? Definitely. If you look at the right hand side, do a little simple arithmetic, it is equal to 1. So P of 1 is actually true. Now, what is P of 7? So we just practice. Of course, we don't actually need this one. Just make sense of the P of K, this statement, P of n. Now, P of 7 means the left side is n is being 7, right? So 1 plus 2 plus all the way up to 7. So 1 plus 2 plus 3, 4, 5, 6, 7. Basically, that's the left side. The right hand side is 7 times 7 plus 1. So 7 times 7 plus 1 divided by 2. Basically 7 times 8 divided by 2. So that's the P of 7. Okay. And now if you, in general, what is P of K? Then that means when n is k, what is this statement? So it's going to be 1 plus 2 plus, when n is k, okay, that means the last integer is going to be k, equals, the right hand side will be k times k plus 1 divided by 2. That's P of k. And what about P of k plus 1? That means when n is k plus 1. So it will be 1 plus 2 plus, well, plus k. You should not stop here. You should continue plus k plus 1. That's the very last number that you should add, which is k plus 1. And what is this equal to? It is equal to when n is k, right? So when n is k, plug in k, when n is k plus 1. So plug in k plus 1 here. So k plus 1 and times, if you remember, the next is n plus 1. N is k plus 1. So you have k plus 1 and then plus 1 divided by 2. So that's what the P of k plus 1 is. All right. So now after we make sense of like what Pn represents, let's try to prove this statement. This is a formula, a well-known formula, telling us the sum of the first n positive integer is equal to this result. And this formula is called, is in the closed form. Right there, this is in the closed form because there's no ellipsis or no summation notation. So in other words, this is not closed form because there are ellipses telling you the pattern, and this is not a closed form because there's a summation notation there, and this is in the closed form because it's just a simple formula without ellipsis and summation notation. Now let's do this one. So step number 1, we have to check. So step number 1, okay, it's supposed to be, I should write proof. And step number 1 is to prove that, prove P of 1 is true, okay? By the way, I think I should state that n is greater than or equal to 1. This formula should state n is greater than or equal to 1. Definitely n cannot be negative numbers, cannot be 0. You start with 1, right? So greater than or equal to 1. I should put that in here, so I'm going to put that here. Now the smallest n is 1, so we want to prove that P1 is true. Now P1 is true. So first of all, what is P1? We already stated that earlier, like this is actually P of 1, that when n is 1. What does this statement look like? Okay, so prove that this is true, and here's the proof. 1 is equal to 1 plus 1 over 2 is definitely true. It's pretty trivial, don't you think? Because here this is 1, right? The left hand side is 1, the right hand side is also 1, the left side is 1, the right hand side, maybe I'll say the left hand side of my P1 is 1, and the right hand side is actually 1 times 1 times 1 plus 1 divided by 2, which is also equal to 1. So the right hand side, you see that left hand side equals the right hand side. Therefore, let me write it. So P of 1 is true, right? So we, usually the first step is pretty easy. Now step number 2, always keep track of what you're trying to make sense. Make sure that you make sense of the idea, like what do you really need to do. So in other words, let's say for all k greater than or equal to 1. So suppose for all k greater than or equal to 1, assume this pk is true. So you have to assume this is true. So suppose pk is true, okay? In other words, what that means, okay? In other words, you're gonna assume this statement is true. So i.e., assume this is true, right? 1 plus 2 plus all the way up to k is equal to k times k plus 1 divided by 2. Now, that's what we are doing. We are assuming this is true. Okay, we are assuming this is true. We want to show that p of k plus 1 is true. So we want to show that p of k plus 1 is true. In other words, let's make sure that you know what this is. So what is p of k plus 1? That is this. 1 plus 2 plus k plus 1 is equal to, and earlier we did this exercise, right? So it's equal to k plus 1 times the k plus 1 plus 1 over 2. And definitely, if you simplify this a little, it says k plus 1 times the k plus 2 divided by 2, because 1 plus 1 is equal to 2. So that's basically what we want to show. After we assume this is true, we want to show that this is equal to that. If we are successfully show these results, then we can conclude that this formula is true for all n. Okay. Now this is let's begin with so this is what we want to show, right? Let's begin with the left hand side here. The left hand side of the pk plus 1, okay, equals 1 plus 2 plus k plus 1. Now we definitely have to use what we assume, suppose our supposition. So do you see that we have this guy right there? That's the left hand side of my supposition, right? So I'm going to replace this with k times k plus 1 over 2, because that's what we assume. So k times k plus 1 over 2. Okay, that's by supposition, plus k plus 1. And probably now you know why when I write the left hand side of p of k plus 1, I also write the k out, because I already know earlier, I already know that I'm going to take advantage of my supposition. So this is why I write 1 plus 2 up to k and then plus k plus 1, so that I show you this is the left hand side of the supposition. Now do a little algebra. Your goal, your target is to show that this guy is equal to this, right? The right hand side. Okay, so let's add this together. That means you have to find a common denominator. So let's multiply the second term by 1, which is 2 over 2. And let's add. This is going to be k times k plus 1 plus the second term will be 2 times k plus 1. 2 times k plus 1. And do you see that k plus 1 is a common factor? I can factor it out, right? So therefore I have k plus 1 factor it out times k plus 2 left. Now, isn't this is the right-hand side of what we want to prove? That's exactly the right-hand side of the to show. So in other words, according to the mathematical induction, so we show P of 1 is true, and step 2, we show if PK is true, then PK plus 1 is also true. So we have achieved both both statements. Therefore, we can make a conclusion, okay? So therefore, so here's the conclusion. Therefore, 1 plus 2 plus up to n is equal to n times n plus 1 divided by 2 is true. I can now claim that true for all n greater than or equal to 1. That's the end of the proof.